Low-level stratus formation. In this video we're going to consider some of the mechanisms by which low-level stratus forms. On the right hand side you can see a trace which is characterized by low-level stratus, and if you look at that, there's the base is somewhere about 3,000 feet and the top is about maybe 6,000 or 7,000 feet. That's indicated by the low value of dew point depression below an inversion in the trace. So how did it form? Well, firstly you need a moisture source, and very often low-level stratus forms because there's advection of moist low-level air. Secondly, mixing often occurs, and you can mix between two unsaturated air masses and get a saturated air mass. So mixing mixes up air both vertically and horizontally and can produce stratus through a depth. Lifting is also good, and stratus often forms on the seaward side of mountain ranges like the Great Dividing Range, which extends up the east coast of Australia and over parts of southeastern Australia. Lifting gives rise to adiabatic cooling, and so parcels can be cooled to saturation. There is of course radiational cooling as well, and so stratus can form or form more thickly at night when air cools to saturation. And then there's the wet bulb process, which we've spoken about in another video, so that extends the base of nimbostratus or can result in the formation of low-level stratus when there's significant precipitation into a region in the lower part of the atmosphere that's unsaturated but perhaps close to saturation. So there's a number of ways in which low-level stratus can form. Here's an example on the east coast of Australia, and we're looking at something known as a critical location. A critical location is a location through which aircraft flying on what's known as visual flight rules, that is, they need to see the ground at all times, can navigate through the Great Dividing Range. In Victoria it's the Kilmore Gap. One of the locations in New South Wales is Mount Victoria, and the nearest AWS is at Mount Boyce. Low cloud forms at Mount Victoria when there's a moist easterly airflow, and so we have the advection of moisture. And then mixing in the vertical thickens the cloud, and also mixing with environmental air can lead to saturation, as discussed before. Lifting, as the air rises over the ranges and moves from east to west, can force cooling. And then finally, stratus is more of a concern at night because of the extra radiational cooling that's going on. What we have on the right hand side now is a sequence of metadata. So this is hourly reports from the automatic weather station. And you can see the mean direction of the wind is roughly easterly, and then you see the temperature on the left starting at 4.9 and the dew point temperature on the right of the slash starting at 2.9. There's no precise hard and fast rule, but we're going to approximate the formation of low-level stratus when the dew point depression is 1 degree Celsius or less, and you can see that starts at 09 UTC or 09 Z. Add 10 hours to get the local time, and that's 7 PM, and that persists all the way through to 22 UTC the next day, which is add 10 is 32, 8 AM in the morning. So when we're doing aviation forecasting and considering something known as an area forecast, which is an average in space and in time, then we need to consider the critical locations, and a standard value often is 11 Z for the formation of low cloud in a critical location. In this case it formed 2 hours earlier, so clearly one doesn't resort simply to standard values but looks at the weather on its merits. So here's an actual area forecast, and it's area 20, which is for northeastern New South Wales, from 11 UTC to 23 UTC, so it's a 12-hour forecast. And here's a forecast for the critical location for Mount Victoria, with cloud above mean sea level. So conditions for Mount Victoria are 9999, which means there's 10 kilometres visibility in the horizontal, and scattered cumulus at 5,000 feet above mean sea level. So scattered means it's 3 to 4 octaves. From 12 UTC for this particular forecast, broken stratus, so that's 5 octaves or more of stratus at 3,700 feet above mean sea level, And because that is the height of Mount Victoria above mean sea level, they've added the information that means cloud on ground. So this would exclude flying via visual flight rules because pilots would not be able to observe the ground. We can see that there's no accompanying precipitation in this, so the cloud's not forming via the wet bulb process. It's primarily this moist air mass that's being force lifted, producing mixing and parcels reaching saturation as a result, and radiational cooling as well. Here's another couple of examples. On the top we have examples for area forecasts, where again the cloud is above mean sea level. The top line has broken stratus 1,000 to 2,000 feet thick, so it's 1,000 feet thick, and the region in which it occurs is the sea and the coast, and it's occurring after 11Z. So a moist air mass with the radiational cooling leading to this broken stratus. Conditions further inland are not going to be quite as moist, and so we see the scattered stratus, there's less of it, and it's also at a higher base. And then finally the forecast also contains scattered stratus 1 to 3,000 feet in precipitation, and so that will be stratus cloud formed by the wet bulb process. There's also on this slide a TAF, or a terminal aerodrome forecast, so that's a point location forecast. You can see there are three examples of how stratus might be used. The first one has a visibility of 5,000 meters, and rain is occurring, and also broken stratus at 1,000 feet. That's 010. And so this is most likely due to the wet bulb process. And then the other two lines indicate things we'll examine later in the course that talk about how long stratus will persist for. So inter, it's for periods of 30 minutes or less, and tempo, it's for periods of an hour or less. And you can see that different sorts of weather can produce different amounts and bases of stratiform cloud. So a shower of rain out of a cumulus cloud producing 4,000 meters of visibility and broken cloud at 800 feet. And then the other line has 3,000 meters visibility and broken stratus to 1,000 feet in thunderstorms of rain. So there are a large number of combinations that can occur. They're all examples of wet bulb process formed cloud. So that raises the issue of when can we assume that cloud will form via the wet bulb process? Well, if it's going to, we need to ask the question of how much cloud there is, but the first question is, what kind of system do we have? How much rainfall do you anticipate? Will it be heavy rainfall or light rainfall? And the region of atmosphere, the low region of atmosphere in which the precipitation is going to fall, how close is it to saturation? If it's not very close to saturation, it's going to take a lot of rainfall to evaporate into that region to produce significant amounts of low cloud. But if the region of atmosphere near the surface is very close to saturation, then it's not going to take a lot of precipitation to saturate it and to form the low-level stratus. So that will have an impact upon how much. Again, cloud base and depth, it comes down partly to preferred values and experience. But the heavier the rainfall, the more intense the rainfall system is, then more likely the lower the base is going to be. But again, it becomes a part not just of assessing the rainfall potential, but also the boundary layer and how close it is to saturation. And then the issue of how long the cloud will last will depend upon things like, what is the dew point depression? So how long will it take to mix that saturated air again with the dry environmental air to produce unsaturated parcels of air? How fast is the rainfall system moving? How intense is the rainfall? And so on. There's a number of factors that you'll develop throughout the course. And as noted before, you can lower the cloud base, that produces nimbostratus, or you can produce a layer of cloud below the main cloud layer, which we call stratus.